Hi. In this paper, we address the task of spoof audio detection in resource-constrained setting using microfeatures. The problem statement is, can the microfeatures of speech be used to differentiate between spoofed and bona fide speech? Our hypothesis is that the fine details of bona fide speech are not replicated well in spoofed speech. We studied two microfeatures, voicing onset time and coarticulation, and build models using these features alone for the detection task. We find statistically significant differences in the VOT and in coarticulation, and we find that models like random forest perform well when trained on VOT and coarticulation individually. What are microfeatures? Microfeatures correspond to measurements typically within time interval of the order of 1 to 20 millisecond. And our motivation is that microfeatures usually do not have direct perceptual correlates. For example, they are difficult to capture by the untrained human ear and are also not captured by typical metrics used to evaluate synthesized audio. And spoof detection systems in place today are space and memory expensive systems. Therefore, effort should be made on cheaper systems built on simple to extract audio features to act as reliable pre-screening for spoof audios. For our experiment, we use ASP Spoof 2019 dataset. Here we show the scatter plot for 4 speakers. Observe that while there is an overlap in the spoof and bona fide voicing onset times, spoof audios exhibit much larger variation than bona fide audios. The VOT of bona fide audios ranges from 0 to 100 millisecond, whereas for spoof it ranges from 0 to 250 millisecond. We use VOT to train 3 machine learning models, and we use different subsets of the stop phonemes to do the classification based on whether it is voiced, voiceless, whether following vowel height is high, mid, low, etc. The table shows that the F1 macro achieved using random forest on the subset E forms the best, which consists of all the stop phonemes followed by a low vowel, and the best F1 macro is 1.5%. Here, we show some of the differences in the formant movements for selected phonemes. The figure illustrates high rate of formant movements in bona fide as compared to the spoof utterance. We use coarticulation features as separate features alone to train 3 ML models. F1 velocity is a change of the first formant over a duration, and we find that it is the most distinguishing feature and gives us the best F1 macro. Here we compare the benefit of using the microfeatures in addition to the state-of-the-art constant Q capsular coefficient features in deep learning framework. And we find that microfeatures improves the overall performance of the models. But of course, random forest models are computationally much cheaper. This is a summarized version of our work. For details, please look at the paper. Thank you.